A few years ago, Numberphile published a video about a bowling ball colliding with a ping-pong ball that would then bounce off of a wall and return to collide with the bowling ball. This process repeats until the bowling ball comes to a stop. The video made a remarkable claim that if the bowling ball's mass is related to the ping-pong ball's mass by 16 times 100 raised to an integer power, and you count the number of collisions it takes to get the bowling ball to stop, you'll get the digits of pi out to the integer plus 1. The math for this claim is complicated, so I've made a computer code to simulate the process and show that it works. The first thing we have to do is set up this very special mass factor. So in order for this to work, the ratio of the two masses has to be 16 times 100 raised to an integer power. So we're going to start with an integer power of 1. So the mass ratio will be 16 times 100, or 1,600. And this is supposed to give us the first two digits of pi. So we should be looking to get out 31 collisions at the end here. We create our small sphere, we're going to call it small, and our big sphere, we're going to call it big. We're using VPython's sphere command that automatically creates a visual for us. The absolute necessities we need to give these things are a position, a size, a radius, and a color so we can tell them apart. So the white one's going to be smaller, the red one's going to be bigger. Of course, you'll be able to tell their difference in size visually as well. And we're appending some extra physical properties that aren't usually part of the sphere, but we can append whatever we want onto these things. So we're giving each of them a velocity vector. The small one is going to start out at rest. The big one's going to come in moving to the right. Notice it starts out to the left of the small sphere, and so it has to move to the right to collide with it. And we give the small sphere a mass of 1 and the big sphere a mass of the small mass times the mass factor. So in order to change the mass ratio, we just have to fiddle with this number up here. We don't actually have to change anything about small and big down here. And then, of course, we need the boundary, the wall for the small sphere to bounce off of. That's our box here. We're placing that 5 units over to the right, and we're giving it a little bit of a size so that you can see it. Now, you may have noticed in the Numberphile video that they don't specify the distances for these things. It's independent of the distance, so I just picked 5 and -5 just to make things symmetric, but those values don't matter. They cancel out in the end. We're interested in counting the number of collisions, so we create a counter here called collisions. We're going to set that initially equal to 0. And as always, with the Euler-Kromer method, we need a small step size. The next thing we have is the loop that implements the Euler-Kromer method. Basically what we do is we replace the current value of the position with the current value plus the velocity times dt. This is the basic Euler-Kromer method applied to position and velocity. If you're not familiar with that, check out the tutorial in the description below. The only complicated part to this is the collisions. So we have to check for collisions between the spheres. So here we're checking for whether the two spheres have overlapped with each other, in which case we're implementing the rules for a perfectly elastic collision that conserves both linear momentum and kinetic energy. And basically you can look these formulas up online, but basically they're kind of symmetric. There's always a piece that involves a difference of the masses, and then a piece that involves 2 times the other mass in the object. And that's basically the two formulas are symmetric. Very nice how they work out together. And we basically replace their velocities with these new velocities. Now for colliding with the boundary, we don't have to worry so much about all of this stuff. We just flip the small sphere's velocity. So we just set its velocity back in the other direction. And it's at that point we're going to count the number of collisions. Now I don't remember in the original video whether they're counting the number of collisions with the ball or the number of collisions with the wall, but they're the same number, right? So for every collision with the wall, there's going to be a collision with the bowling ball. So it doesn't really matter which way you count it. And then we're going to run this loop for as long as the bowling ball, the big sphere, is moving. So as long as it's moving to the right, we'll keep looping over this. As soon as this thing stops or turns around, we exit this loop and then print the number of collisions. So again, we've got our integer value up here set equal to 1. So we should get out the first 2 digits of pi, 3 and 1, to make 31. So let's run the code and see what happens. I should mention that as with all my codes, the The source code is available at a link in the description below. All right, here comes in our bowling ball. We get our first collision. Of course, the smaller ball, the ping pong, is bouncing off faster because momentum is mass times velocity. So when this thing transfers some momentum, it's transferring velocity. Okay, we've got some collisions going on. We're getting more and more collisions until we finally get 31 collisions as predicted. Now, what I find interesting about this result is that it's the first n+1 digits. It's not the first n+1 digits rounded. Not that this would be rounded differently, but I find that interesting that it's a truncation. Let's flip back over to here. Let's increase this to 2, see if we can get the first 3 digits of pi. So do we get 314 collisions? So you notice the bowling ball is moving in with the same speed that it did before, but keep in mind, it's now got 10,000? No, excuse me, it's now got 100. Yeah, it increases by 100 every time. It's now got 100 times the mass. So this white ball, the ping pong ball, is going to bounce off faster. And that's why you're able to get more collisions. Yeah, we're definitely getting more collisions. We got 314 collisions. So there are your first 3 digits of pi. Now, I have tested this thing out off camera, and I found that I can go up to 4 successfully without the code glitching on me. Basically, if you put this thing higher than 4, then the change with each collision is too great for the time step for it to run in a reasonable amount of time. So let's up this thing all the way to 4, see if we can get 5 digits of pi. So we should get lots and lots of collisions. So this thing now has 16 times 100 to the 4th power the mass of the ping pong ball. So this is a super dense bowling ball meeting a very light ping pong ball. There goes the ping pong ball. And we're bouncing off. We're going to get more collisions. Going to get more velocity. There we go. And lo and behold, we get 31415 collisions. So there you have it, this nifty way of getting pi from a physical process, illustrated for you here with simple computer code. How many lines is this? With just 38 lines of computer code. Feel free to open this link, make a copy of it, and play around with it, see what values you can get. And can you get higher than 4? That would be nice to see what kind of tricks we can pull to get this thing to work for an integer higher than 4. Thank you so much for watching. I will see you next time. Bye-bye.